Hello everyone, here's some more problems, this time coming from section 1110, and I think I might divide 1110 into a couple sections of problems. So this video will mainly deal with making Taylor and Maclaurin series for functions. So meaning we'll be given a function and asked to find the Taylor-Maclaurin series centered at some number, okay? So let's dive right in. So let's consider the Maclaurin series for f of x equals, how about e to the negative 2x? And then let's see, how about radius of convergence as well? Okay, so remember Taylor series, Maclaurin series, these are all based on the derivatives of our function. Okay, we're assuming we have an infinitely differentiable function and we just find all these derivatives, f0 meaning, okay, we don't even, it's just the function itself, it's not actually the derivative. F1 being the first derivative, F2 being second derivative, and so on. Okay, so remember our Taylor series, our Maclaurin series, they have this form. Okay, this is the form for a Taylor series centered at A, right? And remember that Maclaurin series is just a Taylor series centered at 0. So our formula for, if you're going to memorize one formula, I would memorize this one. And then just remember that when they say Maclaurin series, A is 0. Okay, so we want this thing, okay, for our function e to the negative 2x. So let's start by just finding a bunch of derivatives for e to the negative 2x and see if we can spot a pattern. We do need to spot a pattern for this. Okay, so first derivative. What's the first derivative? Negative 2e to the negative 2x. What's the second derivative? Positive 4e to the negative 2x. Third derivative. Negative 8e negative 2x. Fourth derivative. Positive 16 e to the negative 2x. Okay, so maybe this is enough to spot a pattern. Okay, look at starting here at the first derivative. We got negative 2, positive 4, negative 8, positive 16. So we obviously have alternating sign, right? And let's see, at index 1, we have a negative. Okay, so that should be negative 1 to the n. And then what do we have? We have 2, 4, 8, 16. That's powers of 2. So is it 2 to the n, 2 to the n plus 1? What is it? Well, again, at index 1, we have 2, which is 2 to the power 1. At index 2, we have 4, which is 2 squared. Yeah, so we should just have 2 to the n. And then what do we have? We just have e to the negative 2x in every one of the derivatives, right? So in general, we can say that the nth derivative is negative 1, 2 to the n, let's see, negative 1 to the n, 2 to the n, e to the negative 2x. And we want the nth derivative, and we want to evaluate it at 0, right? So when we plug 0 in for x, that term is just going to be 1. So our nth derivative evaluated at 0 is just going to be negative 1 to the n, 2 to the n. Okay. So this is the coefficient for our Taylor series, okay, or our Maclaurin series. So our Maclaurin series should just look like this. Simple. That is our final answer. So this is our, this term, just to reiterate, that this numerator is our f of n evaluated at 0. This is our n factorial, and this is our x to the n. So cleaning this back up, our final answer is this. All right, so we said this is our Maclaurin series for our function e to the negative 2x. What is the radius of convergence, interval of convergence? To do that, we just do ratio test. Okay, since we're doing absolute values, we can ignore negative signs. Okay. So let's see, simplifying this, we would get 2 okay, and we want this limit to be less than 1. So first we ask, what is the limit? Okay, well, let's treat x like it's fixed, then we have 2 over n plus 1. The limit's always equal to 0, right? No matter what x is. I can pluck in x equals 100 million, x equals 4, it doesn't matter. The limit's always going to be 0, okay? So when the limit's 0, whenever the limit of our ratio test is 0, that means it's going to be convergent for all x. Our Maclaurin series, in this case, is going to be convergent for all x. So how would we write the interval of convergence if it's convergent for all x? Well, that'd be negative infinity to infinity, all real numbers. What about the radius of convergence? That would be infinity. Okay, let's consider a Taylor series problem, not a Maclaurin series problem. So how about a excuse me, sorry about that. So let's consider a Taylor series. So Taylor series, not Maclaurin series. I mean, you can think of them as the same thing, but Taylor series for ln of x centered at a equals 2. All right. So what do I need to do? First, I need to find the derivatives of my function. Okay. So let's see, derivative of ln of x, well, let's see, 0 derivative, so meaning just the function itself, would be just ln of x, right? F1, first derivative, would be 1 over x. Okay, what's the second derivative? Okay, maybe it will help to say that 1 over x is x to the negative 1. Second derivative, negative x to the negative 2. Third derivative, 2x to the negative 3. Fourth derivative, negative 6x to the negative 4. Fifth derivative, positive 24x to the negative 5. Okay, so that should be enough. And then let's see, we need to evaluate all these at a equals 2. All right, so let's see, f0 of 2 would be ln of 2, and we won't try and simplify that at all. F1 of 2 will be, let's see, 1 over 2. Okay. So this is where we should start. We should start looking for a pattern in these terms. Okay. I can kind of tell you right off the bat that the first term is not really going to fit our pattern. Sometimes we have to split off the first term and write it by itself. So let's try and focus on finding a pattern in these terms. Everything, so starting at not index equals 0, but let's start here at index equals 1. Okay. So I have 1 over 2, negative 1 over 4, 2 over 8, negative 6 over 16. Okay, so I have fractions, so usually it's helpful to try and consider numerator and denominator separately. Okay, so let's consider numerators first. I have 1, negative 1, positive 2, negative 6, positive 24. Okay, so first of all, I have an alternating sign, and let's see, it starts positive here. Okay, so at index 1, it's positive. So it should be negative 1 to the n plus 1 or minus 1. Okay, just making sure that at index 1, we have a positive number. Okay, so when we plug in n, 1 for n, that should be an even power of negative 1. Okay, and then what else is going on with the numerators? We have, forget about the positive negatives, just look at the numerical part of it. We have 1, 1, 2, 6, 24. What does that remind you of? It's a factorial, right? This is 0 factorial, then 1 factorial, then 2 factorial, just to make it clear. We have 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. So let's see, at index 1, we have 0 factorial, so it should be n minus 1 factorial on top. And then what about the denominator? Let's see, we have 2, 4, 8, 16, 32. So powers of 2, at index 1, we have 2 to the power 1. So how about 2 to the n? Okay. So these are our terms starting here, right? And then we would have this first term that doesn't really match our pattern. Okay, so let's just clean everything up a little bit. So how could we write this series? Okay, so if we have a first term that doesn't match the pattern, what I'm going to do is just pull that out front. Okay, so I have ln of 2, and then I'm going to try and write the rest as a series. Okay, and just to be clear, let's see. Since I'm trying to write a series like this. Okay. At index 0, let's see, this would be 1, this would be 1, and then, okay, the first, when I plug in 0, I get ln of 2. Okay, so ln of 2 by itself should be my first term, and then I can write the rest as a series starting at 1. And then for the rest of that series, my terms match this pattern here. Okay. So let's see, the fn part, just the fn part is going to be this. Okay, so let's write that. I got negative 1 to the n plus 1. N minus, I'll actually come down here where I can write it with a bit more room. Okay, so I have ln of 2 plus series starting at 1, negative 1 to the n plus 1, n minus 1 factorial over 2 to the n, and then that's all over n factorial, right? The n factorial coming from my formula here. Okay. So this part is just my fn, and then this is my n factorial, and then I still need my x minus 2 to the power n. Okay, so now the rest of this is just simplifying our power series. So I'll keep my ln of 2 like it is. And then, let's see, this, I'll show this in several steps. Just so we're not too cluttered, I'll erase this. Okay, so first simplification would be this, all right? I just combine the denominators of my fractions. And I get this, okay, n minus 1 factorial over n factorial. I could simplify that as -1 to the n plus 1 over 2 to the n times n and x minus 2 to the n. Okay, and that's probably as simple as I can make this. So this should be my solution for my Taylor series centered at x equals 2. And then the next thing we could do is ask about radius of convergence. Okay, so we're just going to do ratio series applied to this series. So trying that, I get, again, ignoring any negative signs, I would have x minus 2 to the n plus 1 over 2n plus 1, n plus 1 times 2 to the n times n over x minus 2. Simplifying that, kind of grouping similar terms. Okay, I should get x minus 2 over 2 times n over n plus 1, and I want that limit to be less than 1, right? Okay, this constant, this ln of 2 shouldn't make a difference. I can just ignore that and just consider the series. Limit of this part is 1, and I want the rest of it to be less than 1, right? So I want x minus 2 over 2 to be less than 1, meaning I want this, and then solving for x in my inequality. I should have this, and then adding 2 to both sides to get x by itself. Okay, I have x is less than 4 but greater than 0. So this problem just wants the radius of convergence. So I don't need to worry about testing the endpoints or anything. So I can say without a doubt the radius of convergence is 2, right? I look at this interval. Okay, it's gonna, maybe the endpoints will be 0 to 4, or maybe it'll be 0 to 4. And meaning the end caps are gonna, depend on our series, but we know the numbers are gonna be 0 to 4. Okay, so what's the length of that interval? It's 4 units. We divide that by 2 to get the radius. Radius of convergence is r equals 2. All right, so let's consider a new power series, or excuse me, a Taylor series for a new function. Sorry about that. How about f of x equals cosine of x? We want to find a Taylor series for this. And Taylor series, not Maclaurin series, so a center that's not 0. So how about we try it at center a equals pi over 2. Okay. So first thing we need to do are to find the derivatives of our function. Okay, f0, 0 derivative, meaning just the function itself. That would just be cosine of x. Okay, f1, that'd be negative sine. f2, negative cosine. f3, positive sine. f4, positive cosine. Let's do 2 more. f5, negative sine again. f6 equals negative cosine. Okay, so these are our functions, and we want to evaluate them at pi over 2, right? So f0 of pi over 2, plugging pi over 2 into cosine, I get 0. Okay. If I plug it into negative sine, I get negative 1, 0, 1, 0, negative 1, and 0. Okay. So this is the stuff I want to look for a pattern on, and I can see it pretty easily. The hard part's going to be maybe making a series out of it. So I got 0, let's see, 0, negative 1, 0, positive 1, 0, negative 1, 0, positive 1. Okay, so the even numbers, the even indexes are 0. And then the odd ones, alternating sign, right? Starting on negative. Negative 1, positive 1, negative 1, positive 1, alternating sign. Okay, so how can I write this power series? Let's try and write it out term by term first of all. Okay, so remember I'm trying to write something like this. All right. So let's see if we can write it out term by term first of all and see if we spot a pattern. Okay, if we plug in, let's see, the first index would be f0. Okay, so first thing would be 0. And then I'd get -1, -1 over 1 factorial, right? X minus pi over 2 to the power 1. Okay, then I'd get 0. Then I'd get plus 1 over 3 factorial, x minus pi over 2 to the power 3. Then I'd get plus 0. Then I'd get minus 1 over 5 factorial, x minus pi over 2 to the power 5. Okay, and so on. Now, when I get something like this, how do I write this as a series? Well, the zeros don't really affect anything, right? I can eliminate those. Okay, so let's eliminate those and rewrite our terms and see what we get. Okay, so I get these. Okay, so can I make this into a series? Can I write this as a series? I can spot a pattern on all this stuff pretty easily, right? I got, look at the numerators of our fractions. I got -1, +1. I could write this as plus -1. Okay, so I got -1, +1, -1. Okay, so that's going to be an alternating sign. And let's see. It starts with a negative, so we could write this as a series starting at, let's see, we could do 0 or 1. Let's say it's at 0. Okay, then actually let's say it started at 1. If it started at 1, then I should have, my first term should be a -1 to the power 1, right? And then let's see, what about the denominator of our function, our fractions? I got 1 factorial, 3 factorial, 5 factorial. So it's odd numbers to the factorials of the odd numbers, right? So how can I write that? Well, I know it's going to be something factorial in the denominator. How can I write these odd numbers? How about this? If I wrote 2n, that would always give me an even number, right? And then I could do -1. Okay, that should be an odd number. So let's see, when I plug in n equals 1, I get 2 times 1 minus 1. So 1 factorial. And then if I plugged in the next number, 2, okay, I get 2 times 2, which is 4, minus 1, which is 3 factorial. Okay, that's good. And then I can see if I continue that pattern, I get 5 factorial, 7 factorial, and so on. All right. So I could write these denominators like 2n minus 1 factorial. And then what do I have? I got x minus pi over 2 to the power 1, x minus pi over 2 to the power 3, and so on. Okay, so I got x minus pi over 2 to odd powers. And I could write that as 2n minus 1, x minus pi over 2 to the power of 2n minus 1. So I can write these terms as this. Okay, so my series, this should be my Taylor series in general. All right, so I just eliminate all the 0 terms, and then I make a series out of what's left over. All right, so this is my power series. I could have also started this series at 1, or excuse me, at n equals 0. Okay, so remember our trick for adjusting our starting point of our series. If I want to subtract 1 from this part, okay, I just add 1 on the inside. Let's see, so this should have been n, right? Let's see, so this would be n plus 1, and this would be 2n plus 1. So either one of these wouldn't be an acceptable answer. And if you wrote out the first several terms of both of these, you would see they're the exact same thing. Okay, let's do another problem. How about finding a Maclaurin series for the function x e to the negative x? Okay, so remember Maclaurin series, we're centered at just a Taylor series centered at 0. So we're considering this centered at 0. Now, something that'll save us a lot of time, okay, I got x e to the negative x here. So if I followed my usual pattern of like finding derivatives, right, f0, f1, maybe since I have x e to the negative x, that would get cumbersome with product rule, finding the product rule of a bunch of these. But think about it like this. I could find a power series for this thing, e to the negative x, and then just multiply it by x. Okay, and that should give me the same thing. Okay, so let's forget about x e to the negative x and just consider e to the negative x. All right, let's consider this for a second. F0 is e to the negative x, f1, negative e to the negative x, f2, e to the negative x, f3, negative e to the negative x, right? And then I'm evaluating these at 0. So f0, 0, well, that'd be 1. And then I'd have negative 1, positive 1, negative 1. So we can see pretty quickly it's just an alternating sign term. Okay. So this fn should be, let's see, negative 1 to the power n factorial, and then I got x to the n, right? So this should be my power series for e to the negative x, but I was looking for the power series for x e to the negative x, so I should just multiply this by x. Okay, and like in section 11.9, okay, if I have a power series with something on the outside, I want to bring it inside. Okay, and I get this power series, and that should be my final answer. And maybe the book writes it differently. Maybe the book writes it, instead of starting at 0, maybe they start at 1. It's the same power series, just slightly different form. So if I started at 1, then I would have this. They're the same thing. Either one should be acceptable. So that saved us a lot of time, okay? Instead, like, it would have been really nasty if we did product rule, just an example. If I did product rule on this to find all my derivatives, let's see, the first derivative would be e to the negative x plus, or excuse me, so this would be our f0, f1. Okay, and then f2 would be negative e to the negative x minus e to the negative x plus x e to the negative x. And we can see it's going to get out of control with this product rule, right? So it's a lot easier to just consider this term by itself, find that power series, and then multiply by x at the end.